So I would like to start welcoming you all to the 29th webinar of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the cameras and microphones turned off, except for the moment you're going to speak. Questions will be allowed after the webinar unless otherwise requested by the speaker. The questions can be asked using the chat. Today, we have the honor to listen to Professor Mikhail Iosifovich Katsnelson, who is a member of the Academia Europaea, of the Royal Netherlands Academy of Arts, and of the Royal Society of Sciences at Uppsala. Mikhail Katsnelson received his Master's in Science degree in Theoretical Physics at the Department of Physics of Ural State University in Russia in 1977. Received his PhD and Doctor in Science degrees in Solid-State Physics at the Institute of Metal Physics, Sverdlovsky, also in Russia, in 1980 and 1985, respectively. He got a professorship in Solid-State Physics and in Mathematical Physics in Ural State University in 1992, and in Theoretical Physics in Radboud University of Nijmegen in 2004 in Netherlands, where he has been until today. Professor Katsnelson is known worldwide for his contributions to solid-state physics, for which he received the following recognitions: the Lenin Komsomol Prize, State Prize for Young Scientists of Russia in 1988, Radboud Science Award in 2010, Knight of the Order of the Netherlands Lion in 2011, Honorary Doctor of Uppsala University in 2012, Spinoza Prize, which is the highest scientific award in the Netherlands, in 2013, and the Hamburg Prize for Theoretical Physics in 2016. But we are here today to listen to Professor Katsnelson, so that I won't take you your time further with this introduction. Professor Katsnelson, thank you once again very much for having accepted our invitation. From this moment on, the audience is yours.
Many thanks, Louis, for the invitation and for the very kind introduction. Today I am going to talk to you about some quite recent activity, what we are doing in the field of magnetism, and maybe in a bit more general context of what is complexity in natural sciences. And first of all, of course, I have to mention and thank my collaborators. You see that it's a lot of people all over the world, from Uppsala, of course, from our own university, from my home university, which is now called Ural Federal University, then some people from Moscow, from Manchester, and last not least, with some biologists from the group of Eugene Koonin in National Institutes of Health in Bethesda. So after brief introduction, I will tell you about the problem of pattern formation in physics. I will use magnetic patterns as an example, despite, of course, the problem is much more general. Then I will tell you how we can characterize complexity, structural complexity of various objects. And then, of course, the most important, how we can understand the complexity. We still do not have a complete theory, complete understanding, but at least there is one particular case, so-called self-induced glassiness, where we seem to have also some analytical theory and some numerics. And very recently, this concept was experimentally confirmed by our friends and colleagues from scanning probe microscopy group of Radboud University. And at the end of my talk, I will tell something about quantum systems before it will be all classical. So first of all, complexity is a kind of very important concept, which nevertheless is very difficult to define formally. I can refer just to famous motto about pornography that I cannot define it, but when I see it, I know it. And the same story is with complexity. And of course, when we are talking about complexity in natural sciences, then first of all is biological complexity. Biological objects are supposed to be kind of prototype of complex objects in general. But I am not going, we are working on it, but I am not going to discuss these biological issues in my talk, because they definitely deserve a special detailed discussion. But in principle, of course, one of the most complicated problems of science, like origin and evolution of life, it is actually of the same kind. It is a problem of origin of complexity. But in this talk, I will restrict myself completely to discussion of complexity of inorganic world. And again, complexity in inorganic world is something which is not so easy to define. In part of my talk, I will give you some examples how we are attempting to solve this problem. But intuitively, following this principle, when I see it, I know it, I would say that some patterns which you can see in inorganic world can be definitely considered as something complicated. The first picture on the left side is striped domains in ferromagnetic thin films, picture borrowed from our colleagues and friends, experimentalists from Uppsala University. It is a distribution of magnetization in some multi-layer fields of cobalt and permalloy, and white and black regions show roughly magnetization up and magnetization down. You see quite complicated pattern. The second on the right top part, it is just the photo which I made myself. It is just stripes on a beach, sand patterns in tide zone. And what is, of course, amazing and even shocking, I would say, that you can be sure that when you are talking about distribution of magnetization in magnetic fields, and when you are talking on distribution of sands under the action of waves and so on, you can be sure that physical mechanisms, mathematics, and so on are totally different, but nevertheless, the patterns are extremely similar, which give you some insight that maybe you should think about some kind of universality in pattern formations in completely different systems. It's not also funny, it's also practically extremely important, in particular practical use of structural materials, and the most important material of our civilization, the structural material is steel. And for instance, to use steel with peculiar mechanical properties, you can also, you should create some particular mesostructure, in particular perlitic, so-called perlitic structure. It's also a typical pattern, and definitely we need to have some understanding of all this. So coming back to the question, what is complexity? Okay, as theoretical physicists, we cannot be happy just with this approach. When I see it, I know it. I need to have some definitions. And I have to say that in the recent review by Lloyd, more than 40 different definitions are discussed, which usually means that, of course, you do not have proper definition, otherwise you would not need 40 different. But all these definitions can be very roughly divided into two categories. The first one is so-called computational or descriptive complexities, and the second like structural complexities, effective complexities. Before going to these physical structural complexities, I have to say a few words about computational and descriptive complexities. There are many types of these definitions, but basically it is what is usually called Kolmogorov complexity. It is the length of the shortest description of the object. The object can be very complicated, naively speaking, but if you can build the whole object following some very simple and short instruction, then it is not complex, then it is simple. This is a definition. And this approach is very popular, in particular when people are discussing quantum complexity, then more or less define quantum complexity as a number of gates, a number of steps which you need to derive a given quantum state from some initial fixed state or something like that. So it is a length of instruction. This definition, however, is not completely satisfactory. It has many problems. For instance, there is no way to calculate Kolmogorov complexity. Even if you have some shorted description, generally speaking, you cannot prove that it cannot be some even more short description or something like that. But much more importantly, this Kolmogorov complexity, from our intuitive point of view, in spirit of when I see it, I know it, overestimates complexity of purely random objects. For instance, you can measure this complexity is how you can compress that picture. And on the left side, you see just the picture of white noise, purely random picture. And on the right side, you see one of the most beautiful painting, Vermeer view of Delft painting. And definitely, intuitively, we would like to believe that this right picture is more complicated than just some random noise, but actually if you just see how many space you need in your computer to store this, then actually there is no any essential difference. And also, if you are talking biological complexities, then naively speaking, we can say that instruction in this case in genome, and you can assume that for more complex organisms, you should have longer instruction to build this organism, that is longer genomes than for simpler. But again, it does not correspond to our intuitive definition of what complexity is. In particular, we believe that we humans are something more complicated than just grass. But nevertheless, if you just look at the genome of Homo sapiens and the genome of this nice grass, which is called Paris japonica, then actually this grass has 50 times longer genome than we have. And is it really correct to claim that it is more complicated? Of course, it's a very naive approach because in reality, actually, in genome, you have a lot of junk, you have a lot of non-coding parts and so on, and you need more detailed analysis. And my friend and collaborator, Eugene Koonin, did this analysis. He was trying to estimate, say, contextual, real biological complexity for various groups of organisms. But again, you do not see that it increases during the evolution. If you go from some simple organisms to more complicated organisms, that the density of instruction, say, it actually more or less constant and even slowly goes down for high organisms. So this definition in terms of length of instruction, it's definitely very useful in many cases, but it seems to be not universal. We need another definition. And also what is important, that complexity is not entropy. When we consider more and more random patterns, then of course entropy always grows, and information complexity always grows, because if you do not have any simple rule how to restore the whole pattern, then you really need to describe it point by point, and then the instruction will be very long, as we see. But intuitively, we have a feeling that complexity should have maximum somewhere in between of fully ordered state, like crystals, and fully disordered states. And let's think, can we do this complexity? There are many influential attempts, and in particular, it is very important, this concept of self-organized criticality, introduced by Buck and collaborators. And actually, he made a statement that complexity is criticality, and criticality is fractality, self-similarity. But again, this definition does not correspond to our intuitive feeling of complexity, because again, if you are thinking about biological complexity, you do not see any self-similarity, because if you consider, for instance, our tissues at the level of cells, at the level of cell organelles, at the level of biomolecules, at the level of individual atoms, they do not look similar at all. So actually, I would say the true definition of complexity should be beyond this self-similarity, and this is a definition which I will discuss. But okay, I do not want further to discuss the problem in general. Let's focus on one particular type of inorganic complexity. It is a complexity of magnetic patterns. This is some typical picture borrowed from our paper, which is shown on the slide. It is again this permalloy cobalt multi-layer film. What happens when you go from left to right? Again, these domains, striped domains. You apply magnetic field in plane, and you start with more or less regular domains, and then when you increase magnetic field, you go to some more or less chaotic pattern. And just as an example of the problem which I would like to solve, I would like to have an explanation of such magnetic patterns. You see that they are very different, and you can see some of them quite ordered, some of them quite disordered. It's extremely complicated story, and we still do not have complete theory, but we would like to have it. Good. First of all, we have a good news as theories. Most probably we know the Hamiltonian, and this Hamiltonian looks reasonably simple. So if you consider just field, continuous classical field, distribution of magnetization, which is vector M, then to reproduce these patterns, most probably, you need to add exchange interactions. This is first two terms in the Hamiltonian. Derivatives of magnetization and J are exchange parameters, not necessary anisotropic, but just for to be general, I assume that they can be also different in X and Y direction, but it's not necessary. Then you have single ionic anisotropy with easy axis perpendicular to the plane. Then, as I said, you need magnetic field in plane, and very importantly, you need long range but weak dipole-dipole interactions, which is described by the last term. Why I can be sure that this Hamiltonian is sufficient to reproduce these patterns? Simply because we did classical Monte Carlo simulations with these Hamiltonians, and we see distribution of magnetization, which is quite similar to what is observed experimentally. But again, we cannot be happy with just a bunch of numerical data. We want to have some theory. And I will do it in two steps. First, I would like to have some characteristics, some quantitative characteristics of complexity to describe complexity. Beyond this, when I see it, I know it, and then I would try to explain magnetic complexity. Let me start with the first with the definition of complexity, following our very recent paper. And the idea was, in some sense, opposite to Perbach idea, that we believe that this similarity at different scales is a measure of complexity. And so this is really, you start with some kind of multi-dimensional pattern, not necessarily two-dimensional, and then you do some kind of coarse-grained procedure. You throw away part of degrees of freedom. And then you look at the overlap of initial pattern and coarse-grained pattern. And then you sum up over all the scales of coarse graining, and we believe that the number which you have at the very end, which shows how different is the system at different scales, it tells you something about complexity. So in more technical way, we start with some picture, then we separate it into, in spirit of so-called Kadanov decimation procedure in theory of phase transitions. You divide this picture into pieces, and then you introduce some average color of each piece. You can do it just averaging color all over the piece, or you can use vote. You can just follow the rules. Winner takes everything, and if you have more black than white, then you consider black. You can use also other. There are many ways to do this coarse graining. But anyway, you do some kind of coarse graining, and then you look at the overlap of the pictures. Does it work or not? And let me just check. We consider just some simple photos of different wall stones, and also some abstract paintings. And the numbers which you see at this slide, it is just complexity calculated according to our rule, and it grows on the bottom from left to right, and then when you go on the top, sorry, when you go to the bottom, again it grows. I would not say that at least it does not contradict to our intuitive definition which picture is more complicated than this one. For sure, obviously this nice stone wall is more complicated than just simple brick wall. Okay, then a prototype example is we theoreticians, what we did just experiment. It was just really a solution of die drop in bus tube of water. And so then we did some kind of high resolution pictures, and then we looked at the complexity. And of course, entropy grows all the time. During this process, actually, it is a prototype example how we explain to our students second law of thermodynamics, one of the examples. But complexity behaves in a reasonable way. It has maxima somewhere in between, and I would say that our definition more or less corresponds to our intuitive definition of complexity. Okay, then we switch to magnetic systems, and first of all I have to say that apart from purely aesthetic, how to say, feeling that it would be great to have some nice definition, it's also practical, because for instance we have checked that we can use our definition to find temperature of magnetic phase transitions. There are of course other methods like so-called Binder cumulant and so on. I do not have time to explain, but actually we did simulations in two-dimensional and three-dimensionalizing model, and then we have shown that if you calculate our complexity and its temperature derivative, it has very clear maximum at the point of phase transition, and it gives you very nice estimate of this temperature of transition, which is not trivial because you deal with finite systems. But nevertheless, it works pretty well. I would say it is, mildly speaking, it is at least as efficient as Binder cumulant, and also it's quite easy to calculate. Let's come to true magnetic patterns, and we consider just this kind of Hamiltonian when you have exchange interactions, the Washinsky-Maria interactions and magnetic field. Then you have all kinds of complicated labyrinth structures. And then we studied complexity. And first of all, what is funny, these three pictures are quite different. But this difference, again, intuitively, it is not relevant. They definitely describe the same kind of object, the same kind of structure. And indeed, they have extremely similar characteristics of complexity. So in this sense, we are probably on the right way. And then when we consider, when we change magnetic field and we calculate complexity, that again, I would say we see that our complexity is in agreement with our intuitive definition, which magnetic structure is more complicated than which one. And again, if you calculate, for instance, derivatives in magnetic field, that it is also a nice tool to find transitions from one point to another. I do not have time to explain details, and I refer to this PNAS paper, because strictly speaking, of course, you have much more information if you use not just by number, but the whole function of lambda, the whole integrand function as a function of the scale of coarse graining. But even this simple final answer gives you already something not bad. Also, we did dynamical simulations using, by the way, UFPA code, the spin dynamics code, which was developed by our friends and collaborators from UFPA. We solved just spin dynamics equation, and we looked at dynamical effects, the effect of time-dependent magnetic field, which in practice can be created by so-called inverse Faraday effect. And then again, we consider time evolution of these magnetic structures, and we looked at the complexity. And again, I would say that our intuitive definition of complexity looks like, first, in agreement with what we can calculate, and second, what we can calculate also is a good number showing the change from one regime to another. So I have a feeling that we have a way how to characterize magnetic complexity of magnetic patterns. And now I switch to maybe more ambitious part of our research, how to explain this complexity. And we still do not have complete theory, but I do believe that we had some progress. With particular kind of patterns, so-called chaotic patterns, which appears when you have very high in-plane magnetic field. And the crucial point is a competition, interplay of long-range but weak dipole-dipole interaction and short-range by strong exchange interactions. Because in normal situation, like in Ginzburg-Landau theory, if you do not have long-range interactions, then of course the energy of fluctuations grows quadratically usually with the wave vector of the fluctuations. But if you take into account magnetic dipole-dipole interactions, they force system to have total magnetic moment equal to 0. Otherwise, you will pay a lot of energy for magnetic field outside the sample, and you do not want to do it, right? And so it means that these magnetic dipole-dipole forces, they favor inhomogeneity. And as a very result, if you put them together, you have some kind of Q star, some kind of optimal wave vector of the fluctuation, and it is non-zero. So the system wants to be self-modulated with this Q star, but it does not know in which direction it wants to be self-modulated. And in this situation, you can explain a chaotic pattern. And with Alessandro Principi, who is currently in Manchester, in that time he was in my group in Nijmegen, we did a couple of papers when we applied the concept of self-induced glassiness, which was suggested some time ago by Jörg Schmalian and Peter Valinis for striped glasses, like striped glasses in high TC superconductors. We modified and applied this system to magnetic, and it seems to be a successful attempt. First of all, what is glass? Glass is a system with very complicated energy landscape, which characterized of a lot of minima of energy, local minima, and with some fine structure when you can find minima of minima, minima of minima of minima, and so on and so forth. And from experimental point of view, this means that when you go up and down in your parameters, for instance, in magnetic field for the case of spin glasses or in temperature, you never go exactly to the same minima. You go to some nearest minima, and then you travel slowly. You travel slowly along the whole landscape, and your properties will be changed slowly from one thermocycling to another thermocycling. This is a property which is called edging. But very important is that in conventional theory of glasses, and especially spin glasses, disorder, some extrinsic disorder was considered as a very important component. And in our work, we suggested and proven to some extent that you can have this state without disorder for purely deterministic system. We use some formal criterion of glassy state, which was developed by Monason, and the idea is that if you have many local minima, then the system can be glued by external field not only to one particular state, like we have with spontaneously broken symmetry in ferromagnet, when you have spin up and spin down state, and you apply magnetic field, and then the system is chosen to be spin up. But the same story should happen with with infinitely many minima. With so many minima that when you integrate over all space of this minima, you still will have a kind of broken symmetry. This is criterion. Then we applied it with this Hamiltonian, with dipole-dipole interactions and exchange interactions and other. I do not have time to explain technicalities, but at the very end we found phase diagram. So indeed we found that there is some region of parameters, magnetic field divided by magnetic anisotropy parameter and temperature divided by J, when you have this glass phase. And this glass phase is not structureless, it is characterized by some structure with a maximum of structural factor at wave vector, which exactly corresponds this this compromise between dipole-dipole and exchange interactions. And the same story happens when you have only dipole-dipole, sorry, not dipole-dipole interactions, but only exchange interactions. But if these exchange interactions have a kind of Mexican head potential, have a line of minima instead of just one single minimum, what sometimes is called Brazovsky model, then also you can have configuration of entropy, you can have glass states. And I'm extremely happy this concept we suggested in 2016, and in 4 years, together with our collaborators, this is its experimental group where the work was done, group by Alex Khachaturian, and also with our collaborators from Uli Eriksson group in Uppsala, we discovered these states in real system, and it turns out to be a very simple system, namely just elemental solid, elemental neodymium at very low temperatures. That is why you can be sure that disorder is absent, and actually we spent a lot of time trying to check that disorder is really irrelevant. But what we found quite experimentalists, of course, our colleagues, found quite complicated magnetic patterns, and more importantly, edging. That when you go up and down, when you make cycling in magnetic field, you never come exactly to the same point. So in this sense, I would say that this concept of self-induced glass is confirmed experimentally. And very importantly, that also we can have some theory. Calculations were done in Uppsala group. It is based on ab initio calculations of exchange integrals, which can be done using some method which we developed with Lichtenstein and others long ago. And then you can see the energy, potential energy, and you really see that it reminds Brazovsky model. It have a line of minima, and then you can study spin dynamics again, doing simulations of autocorrelation function, and you can compare this with a prototype spin glass system, this copper manganese, and you really see that this dynamics is the same. Okay, but actually, if we are talking about true complexity like biological complexity, then there is some problem. We do not agree with the concept that life matter is glass. It should be more complicated than glass. And this is what we did with our colleagues biologists. But again, I will be talking on something which we physicists understand much better. Recent work what we did about simulation of extremely simple system. It is just Ising model with only exchange interactions. And these exchange interactions are oscillating following RKKY. So it is just very realistic system in the sense that you can put some magnetic atoms at the metal surface, and then we will have this kind of interaction with a parameter determined by the Fermi surface diameter. And this ratio of lambda oscillation period to the lattice constant is the only parameter. And what we found doing just simulations, that apart from self-induced glass state, which we confirmed, and just conventional double well state, which is just ferromagnet, in between you have some multi-well state, which is a bit more complicated because you have many minima, but not so much as you have in the case of glasses. And more specifically, if you look just at the numbers of minima as a function of numbers of sites in the system, that I would say, preliminary, we can say that most probably in spin glass state it grows exponentially. In double well state, it of course does not grow at all, but in multi-well state it grows sub-exponentially, most probably in power law. We still do not have any analytical theory to explain these general considerations and explain these numerical results, and I do believe that it can be very important. And at the very last part of my talk, what I was talking before was about classical systems. Now let me switch to quantum systems. What we can say about complexity of quantum systems, again, it is based on some very recent work which we did. And the point is the following. Suppose you have a spin system, and you are interested in the ground state of this spin system. And generally speaking, of course, to find ground state, it's very, very complicated problem, generally much more complicated than, for instance, calculating single particle and two particle grain functions, what we usually do. And the best way to calculate it, to use some kind of direct variational ansatz. So we probe ground state as an expansion in some basis, and generally speaking, this, of course, coefficients in given basis, they are characterized by amplitudes and phases, or for non-complex Hamiltonian, just amplitudes and signs. And the key point is that could you do it with reasonably small basis? Otherwise, the method is useless. And this dimensionality of basis k, it should be much smaller than the full dimensionality of Hilbert space for the system. And it was a breakthrough in this variation of approaches based with recent paper by Giuseppe Carleo and Matthias Troyer, when they suggested to use some kind of machine learning algorithm to optimize the choice of this trial basis and to find the ground state. And what we studied, we know from our experience with classical spin glass, we know with our experience that frustrations, competing interactions are crucially important. In particular, it was competition between different types of exchange interactions for the case of neodymium, or between exchange interactions and magnetic dipole-dipole interactions for the case of striped glasses. And we consider just Heisenberg model on different types of lattices, square lattice, triangular lattice, Kagame lattice, with nearest neighbor and next nearest neighbor exchange integrals. So we know that varying these parameters, you are always, you can have both regular ordered states and some kind of disorder spin liquid kind states. And for instance, if you have 24 spins, that's the full dimensionality of your Hilbert space. What you need is millions. And we consider much smaller training set, much smaller dimensionality of this variational basis. And we were trying to understand, is it possible to train a neural network to find the true ground state? And it turns out, not unexpectedly, that this is crucially dependent on what kind of system do you consider. Is it frustrated or it is not frustrated? What we looked, the system is not very big, so we were able also to calculate using exact diagonalization exact ground state, and we were looking on the overlap of our trial ground state with exact ground state. Of course, if our trial ground state is ideal, then this overlap will be just one. And you see that actually for non-frustrated systems, beyond this gray region when you have frustrations, when you have spin glass state, you can train your neural network very well using reasonably small training set, and you can describe with extremely high accuracy, the true ground state. But if you are within this region of frustrations, then you fail, especially for Kagome lattice. So it simply means if you study separately, training separately amplitudes of these coefficients and sign coefficients, by the way, I forget to say that the problem is with signs. It simply means that sign structure for this frustrated system is highly irregular. There is no any simple rule which neural network can find itself during training process, how to reproduce for frustrated systems the sign structure. On the other hand, it is not completely random. We did just experiment when we consider purely random distribution of signs in these trial states. We also cannot reproduce the ground wave function. So it is some rule, but it is some rule which is hidden very deeply, which you cannot find easily, and neural network cannot find it very easily, which again, I believe, is something related to complexity. Again, like in classical case, we believe that this data tells us that frustrations lead to complexity, but of course, we need to walk further, and in particular, we need to generalize our definition of complexity of classical patterns to quantum case, and this is something what we are working on now. And basically, I think I'm even more or less in time. So I am now actually even at the end of my talk, so hopefully we will have some time for discussion. I want to tell you what I think in general of this problem of complexity. Because in 1960s, 1970s, of course, it was a huge enthusiasm about origin of complexity, and the key words and key names like Ilya Prigozhin and René Thom, father of so-called catastrophe theory, and keywords are synergetics and catastrophes, and bifurcations and so on. But from the generic mathematical point of view, it was the idea that you can define complexity of true systems from physics to biology based on theory of dynamical systems. Starting, mathematically speaking, some systems which are described by ordinary differential equations, non-linearity, introducing some attractors, and so on and so forth. And it was a lot of enthusiasm. And typical problems which can be quite successfully explained in this approach, it is so-called binary convection cells in heated liquid, or so-called Belousov-Zhabotinsky waves and chemical reactions, and so on. But frankly speaking, I do not think that this approach is very promising. I think we tried. It gave us something, but frankly speaking, it's too large distance from binary convection cells to the origin of life, which would be our final goal or something like that. And what I'm talking about in this talk, it is about attempts of our people, our group and other people, slightly to change the view. So we are trying to understand complexity in inorganic, in particular, in physical systems, not starting from theory of dynamical systems and from the mathematical concepts borrowed from these systems, but from statistical physics. And for us, keywords are not bifurcation, catastrophe, and so on, but rather emergence, renormalization group flow, universality classes, broken replica symmetry, frustrations, and so on and so forth. I did not tell you everything what we did in this direction. In particular, it was very nice activity also about so-called holographic complexity, which is also, in a sense, tells us that complexity is something about dissimilarity of system at different scales. But anyway, I hope I gave you enough of information to think further, and the problem is very far from being solved, but I do believe that this direction is promising, and then I think we should think further, and you should think further, and maybe at this way we will give better understanding of complexity than our predecessors who were working with mathematical apparatus of theory of dynamical systems. Maybe these tools borrowed from statistical physics will give us more. This is a hope. With this, I would like to finish my talk, and thanks a lot for your attention, and I hope I will keep enough of I kept enough of time for discussions and for the questions. Many thanks. That's all.
So, Professor Katsnelson, first of all, I would like to ask everybody to turn on their microphones for a huge round of applause for this excellent webinar. Okay, so as we previously agreed with Professor Katsnelson, he will be able to answer to some questions. He will be able to stay for 15 minutes or so, answering the questions from the audience, both from here and from YouTube. So you can write down your question or even register yourself for questions. But before that, Professor Katsnelson, let me give you an overview of the audience that has been following this webinar of yours. So we have around 100 people from all around, many places in Brazil, like the states of Amazonas, the nearby state to Pará, obviously from Pará State, Rondônia. We have people from Pernambuco and Paraíba from Northeast. We have people from Rio de Janeiro and São Paulo from the Southeast region, and also from Paraná and Santa Catarina from the South region of Brazil, very far from Belém. So we have a wide range of places from Brazil. But not only that, I mean, obviously, this is a webinar promoted by our graduate program. So we have our students, undergraduate and graduate students of our program. We have postdocs, teachers, and professors, like Professor Angela Clautal, Danilo Alves, Valdomiro Pascoal Jr., for instance. Not only people from the capital of the Pará state, but also from other places in Pará, which is a huge state, as you know, the cities of Abaetetuba, Ananindeua, Bragança, Castanhal, Capitão Poço, Santarém. And we have people like Professor Manuel Bezerra Neto from Santarém, Reginaldo Gomes Jr. From the State University of Pará. But not only from Pará, people from many other places in Brazil, as I mentioned, just to cite some of them, Antônio Gil from University of Amazonas, Daniel Menezes from Vale do São Francisco, Daniel Stariolo and Débora Rodrigues from University Federal Fluminense, Edson Moreira from Itajubá, Helena Petrini from USP, José Nascimento from Roraima, Lucas Nicolau from Santa Catarina, Miguel Novak from Rio de Janeiro, Nelson Studa from the state of São Paulo, Newton Branco from Santa Catarina, and Satiscuma from Unirio. But not only people from Brazil only, but also many people from abroad. I can mention Attila Silva, Biplab Sanyal, Christopher Georgeson, obviously Professor Oli Eriksson, Renan Maciel, and also Susan Jacobs from Johannesburg in South Africa, also Ramon Almeida from France, Leonardo Rigon from Busan in South Korea, as far as South Korea, and we have also Igor DiMarco, that I believe he's from Asia. So as you can see, a wide audience distributed from many places around the world that makes us, and I believe you also, very happy. And thank you very much, Professor. So we have here some questions registered. So the first one comes from our PhD student, Danilo Pedrelli. Danilo, would you like to make the question yourself, or do you want me to read it? You already wrote it, but as you wish.
Okay, since you asked that, I'm gonna ask you. I just was wondering, because deep learning usually is treated like a kind of black box, right? So the model learns from data, but usually when you want to understand the parameters and what the model learn, it's a kind of difficult compared to the classic machine learning models. So I would like to ask you, how can deep learning improve the understanding of quantum mechanics, since this is some kind of difficulty, right? And if you have tried other models in your paper too.
Okay. Okay. First of all, there are, I would say, two directions in which it can be some interesting and fruitful collaboration between machine learning, in particular deep learning, and quantum mechanics. First of all, we're supposed to solve optimization problem, right? And from technical point of view, variational approaches in quantum mechanics is a perfect example of optimization problem. You calculate something. It can be, for instance, just a trial energy. If you are talking about ground state energy, the lower energy, the better is your variational principle. Or it can be, as we use, just overlap of trial wave function with exact wave function, in the case when you know wave function, which you can use for training of neural network. It is specific. It is something specific for quantum mechanics. But after you have just these two numbers, it is just optimization problem, and you can use any kind of approaches which you can use for optimization in classical systems, for quantum systems. Simply just the objects which you want to optimize is of slightly different order. It is either trial ground state energy or overlap with wave function or some other quantum characteristics, but from the technical point of view, it is just optimization of some function. In this sense, definitely, machine learning can be used just to have better numbers. On the other hand, this was not in my talk, but I do believe that there is much deeper relation between machine learning and quantum mechanics. And very recently, we published some preprint with Vitaly Vanchurin, who is a well-known cosmologist. You can find this preprint about imagined quantumness in machine learning. So we have proven formally that in principle, very well optimized deep neural network can be described by something which is formally similar to Schrödinger equation, and then you can expect also some completely unexpected, some kind of effective quantumness, some kind of unexpected relations just beyond just having numbers. I have to say, I'm extremely excited about this direction, but we just started, our preprint is just finished just last December, and we are working very heavily on this now, but I do believe that there is some perspective in working and thinking further in this direction.
Okay, so thank you, Danilo, for your question. Thank you, Professor Katsnelson, for your answer. So the next registered question comes from Satish Kumar, VH, from Unirio in Rio de Janeiro. Please, Satish.
Thank you, Nelson. Thank you, Dr. Katsnelson, for the talk. It's beautiful. I don't know much about complexity, but I remember Leonard Susskind saying, if you're not working on complexity, you're wasting your time.
I agree.
So today I did not waste my time because I listened to complexity. So I have a question about the graph you showed about the complexity and entropy in the same plot, right?
Yes.
So how can it's for the ink spreading in water, I guess.
Yes. Let me just find again this slide. Just a second. Yeah, this slide, right? You can see it. This slide, right? Can you see it, or I need to share screen again?
Sure. Yes. And I can see it. Thank you so much. So could you please tell, like, how can we calculate complexity in this case? And do you have one such graph for the spin glass?
Okay, yeah.
Thank you.
Complexity was calculated very basically. Can you see the slide? Structural complexity. You may
yes,
okay. Maybe it's better to explain this. You make a picture. Then you just work with this picture. So you separate it into pieces, right? And you average color over the small pieces. And then you look at the overlap. How this averaged picture dissimilar from the picture. And then you sum up. All similarity overall space. This is how complexity overall space. And what was the continuation of this question? Sorry.
Do you have such a graph of complexity versus entropy for the spin glass?
No, for spin glass, no. We did it for magnetic labyrinth structure. I'm pretty sure that it can be done also for spin glass phase, but I do not have these graphs immediately. But I fully agree that it's worth to do. We should do it. Yes, I.
That's all right. Thank you. Thank you so much.
So thank you, Satish, for your question. Thank you, Professor Katsnelson, for your answer. So we have further questions now coming from another of our graduate students, doctoral students, Rodrigo Azella. Do you want to make the questions yourself? I suggest you make the first and then the second. Please start with the first.
Okay, then. Can you hear me?
Yes.
Yes.
Okay. I see your point in stating the comparison between structural complexity and self-similarity. It seems intuitive, it's okay. But when you state it with fractality, it's not so obvious to me, because when you take, for example, a fractal structure, which is not necessarily self-similar, for example, any kind of random fractal, is it still an indicative of complexity? It seems strange to me that just linearity will give complexity. Is that usual?
Intuitively, I would say that if your system is really the same, at the same scale, when you use the same picture with different resolution, you see the same picture, I would not call it complexity. So ideal fractal like this nice Mandelbrot picture, I would not call them complex. But if you are talking about real systems, it is yes and no, because for instance, I gave example that we calculated complexity for Ising model, for two-dimensional and three-dimensional Ising model, right? And when you go to the critical point where you have some properties of self-similarity, maybe not complexity itself, but at least its derivative with magnetic field or with temperature, it has a very sharp maxima. So in a sense, indeed, self-similar structure, they are characterized by some complexity. But partially it is also because we are working with discrete lattice, and in this sense, the system is not completely self-similar at different scales, because you still have some lattice distance in the systems. But nevertheless, but I do have a feeling that the systems which are not self-similar, which are really different in different scales, they should be considered as more complex, and in some sense our definition is of this kind. Yeah, but I think also, as I said, what I am talking is very fresh. We just started and the paper is published just very recently and so on. Definitely we need to study systematically different types of fractals and to study complexity of fractals separately. I fully agree that it is it's worth to do, but it is not done yet. We should do it.
Okay. Then I will proceed with the next question, Professor Katsnelson, if you allow me. Regarding the Ising model, you commented, I have seen you found successive plateaus. Are they an indicative of time translation symmetry breaking? The graph with many plateaus.
Yes, okay, first of all, there are different ways of calculating complexity depending on how you do coarse graining. I do not want to explain details. Let's look at this blue curve, which I believe is the best. What you see that in the ordered phase, when symmetry breaking happens at very low temperature, complexity is zero, because you have just ferromagnetic spins, and whatever you will do with this picture, nothing happens, right? I mean, they fully overlap. When you consider purely random picture, which corresponds to Ising model at very high temperature, it still has some final complexity, but then this complexity, again, I would say that this definition which gives you plateau is a bit wrong definition. I think the best definition I would say, it is a blue one, which shows that nevertheless you have maximum of complexity in the critical point. But it was exactly to show how details are important. The way how exactly you do coarse graining and how you do this summation, starting from the very beginning or from the first step and so on and so forth. It depends on the details. But I believe that the best definition of complexity, which shows zero complexity for fully ordered states, pretty high, but not the highest possible complexity for paramagnetic phase, and maximal complexity in TC. Again, intuitively, I would say that it is the best definition.
So the analysis on the symmetry breaking is not yet done in this kind of system, right?
Symmetry breaking happens in TC. What you see at the temperature of phase transition, that sometimes complexity itself, sometimes not, it depends on the details, how you define your coarse graining procedure, but the derivative of complexity with respect to temperature always have a maximum in the point of phase transition. In this sense, we feel symmetry breaking. When you have symmetry breaking, you have a maximum of derivative of complexity with respect to external parameter.
Thank you.
Yeah.
Okay, so thank you, Rodrigo, for your questions. Thank you, Professor, for your answers. We have one more question coming now from Sweden. Biplab Sanyal. Please, Biplab, go ahead.
Hello, Misha. I hope you can hear me.
Yeah.
Okay. Thank you for your very interesting perspective of complexity. And I have just a kind of philosophical question. Suppose to me, the most complex thing is our mind, human mind. So where many erratic things happen as a function of time with no correlation at all. So if I want to measure the complexity of human mind, can you characterize that?
It's a good point, because first we need some model of human mind, right? I think now it is a kind of fashion, but maybe also more than just fashion, believe that our human mind is something like neural network. That is why neural networks are called neural, right? People believe that it is something similar. And then in principle, definitely you can study complexity of neural network. And in particular, the last part of my talk, what I did, it was about this. I would say that complex system is a system where it is very difficult to train neural network to understand it. A simple system, and when it is very easy to train neural network to understand this. And in some sense, of course, this difficulty of generalization or more easy generalization also, I think, characterize the complexity. And if you believe that our brain is also some kind of neural network, then I think you can use this concept also to the brain. But whether this is a good idea or not, to say, I think it is better to ask people who are really more competent in brain and biology and neurophysiology and so on. But I do believe that we can characterize quantitatively complexity of neural network.
Thank you. Thank you very much.
So, thank you, Biplab, for your question. Thank you, Professor Katsnelson, for your answer. So before we finish, I would like to thank for this very representative audience from many places around the world. And obviously, thank very much to Professor Katsnelson for this wonderful webinar. And I'll ask everybody to turn on their microphones once again for a final round of applause in acknowledgement for that.